for AI. His recent research focuses on training robotic mobile manipulation systems purely in simulation that seamlessly transfer to the real world. Thanks for joining us, Luca. Take it away.
Awesome. Thanks for having me. Today I'll be talking about building generalizable robotic agents through large-scale simulation. And so just as a little bit of a teaser about where we're going and what I'll spend most of my time talking about, I'll be talking about our building SPOC. So this is the shortest path oracle clone. So SPOC is an end-to-end trained robotic agent that uses only RGB sensors as inputs. That is to say, no depth, no LiDAR, and no map. SPOC is trained purely in simulation and yet transfers seamlessly to the real world with no real-world adaptation or fine-tuning. We train SPOC to imitate heuristic experts that we are able to generate because simulated environments have a rich amount of ground truth data that's readily accessible to us. We are able to do this at large scale. It doesn't require any RL and doesn't require any human data collection. Finally, despite being able to, or training SPOC to imitate shortest path heuristic experts, when we deploy it, it is proficient at long horizon tasks and is able to explore and backtrack and also correct errors that it has made. And so I said that SPOC works in the real world, and here is us taking the agent, again, just trained in simulation and deploying it in our sort of robotic environment. Here the instruction is the natural language instruction to fetch a mug, and you can see that the agent sort of runs around, explores different rooms, eventually finds the mug, and successfully grasps it after a few trials. Okay, so that's where we're going. Let's take a major step back and talk about some of these motivations. So it's almost become a cliche, but I think it's a cliche because it's true, to say that extremely large-scale data sets have been the big driving force between all of the large advancements that we've seen in the last few years in AI. And so in the computer vision space, which is where I come from, we've went from what we used to think was a relatively large-scale data set in ImageNet to truly massive data sets like the Lion 400 million and Lion 5B. And with each scaling up, what we're able to do with these trained foundational models has become broader and broader and more impressive. And so a sort of fundamental question is, what does this mean, or what does it mean to take this seriously for robotics? How do we bring this idea of large-scale data to robotic agents? We're obviously at AI2 not the first people to think about this. And so I'm sure everybody is more than aware about sort of the RT1 paper out of Google, where they're able to train some really impressive behavior with real agents using real data. And here the data set that they collected is relatively large scale, 130,000 episodes over many tasks. But it took 17 months to collect using 13 separate robots. Another approach that's a little bit more recent was this OpenX embodiment data set. And here many labs and institutions came together, sort of pooled all of their data, and were able to generate a large-scale cross-embodiment data set, which is quite impressive, and we're seeing some cool work out of that. So these are great large-scale data sets for robotics, all in real. And because they're in real, they sort of suffer from the fundamental problem here, that if we want to be able to actually scale these data sets up more, if we want another 1 million OpenX embodiment data set sort of instances, or another 130,000 episodes like in RT1, we need to go out and collect these data on robots again. So we need to spend another 17 months and who knows how much time and money to be able to get this data. So collecting data in the real world, it's hard, it's messy, it's expensive. If you really want to collect large scale data, I would make the claim that simulation is king, right? So here is showing a little example from our AI2 Thor environment. That's what we have. And it's great. It's it's incredibly safe. It's fast. You can do all sorts of interesting interactions. And obviously, we're not the only group that thinks that simulators are important and powerful. There are so many interesting simulators out there, like Gibson, Habitat, RLBench, and many more, many coming out every other day. So if simulators are fast, they allow interesting interactions. it must be the case that we can just grab these and sort of solve the scaling issue. And while it'd be great if that was true, simulators are king, but they're also a bit of a disappointment, right? And this disappointment comes in many flavors. The first and perhaps most obvious one is just that there's a lot of limited object diversity in these data sets. So generally, if you want to have a simulator, you need to have 3D assets crafted by artists, and you can only make so many of these yourself. There's also quite a bit of limited environment diversity. So in this AI2 Thor environment that we have, it originally released with 120 scenes in it. And that's great, but it simply does not capture the amount of variability that there exists in the real world. Next, there's the fundamental sim to real gap out there. So this is both visual and sort of dynamical. So you have some agents that just behave in very unphysical ways, and when you try to use them in the real world, they expect to be able to exploit physical behavior that isn't actually sort of accurate. And finally, this isn't really a criticism of simulators, but it's a criticism of how they're used. So since they're fast, a lot of the work that has been using them has sort of used them with RL, with these algorithms that are very sample inefficient. So if you actually would like to train an agent even to do relatively simplistic behavior like this point goal navigation task, to get high performance, you train for billions of steps. And it simply, it makes the scaling problem even harder because now you need to scale the amount of data, manyfold, even beyond what you might expect. So I'll be talking about some of the solutions we have to these problems. So first, for limited object diversity, we've released this Objaverse dataset. So this is a dataset of 800,000 objects that have an extreme amount of diversity and can be used in simulated environments. To address the problem of environment diversity, we have 2 papers along this work. One is ProcThor. So these are procedural environments that we're able to generate and allow us to produce an unboundedly large number of indoor household environments. And then the follow-up work, Holodeck, which takes us a step further. Rather than using hand-built rules for this procedural generation, we instead use LMMs to allow us to sort of generate any environment that you can specify with language. And then finally, there's these 2 very real problems that are the sim to real gap and efficiency. And I'm going to make the claim that these are not going to be a real problem when using SPOC. So we'll see how we get around those in a bit. Okay, so just as a top level outline, we'll be talking about scaling objects, scaling scenes, and then we'll get to SPOC. So again, I'm going to harp on AI2 Thor because that's the simulator that we have. In this environment, we have around 2,000 object instances, which is a good number, that all come from around 108 categories. Yeah, so 2,000 it feels like a relatively large if you need to get designers to create them, but obviously this is a trivial number in comparison to the amount of objects that you might expect a robot to encounter when deployed in the real world. Going beyond AI2 Thor, one of the largest previous existing data sets of 3D assets was ShapeNet. And I'm sure many are familiar. It has like 51,000 instances that come from 55 categories. And this it is an awesome data set. But just looking at it even now, the amount of variability isn't incredibly high. And the objects sort of visual fidelity is also somewhat simplistic. So this brings us to Objaverse. It's a universe of annotated 3D objects that are incredibly diverse and come with all sorts of wonderful annotations. And so like I said before, Objaverse contains 800,000 Creative Commons licensed 3D assets that we collected from the web, and these come with annotations. So these objects come from a variety of different object categories, and these include things that you would hope to have in sort of indoor environments like furniture, art, food, but also contain a whole host of very interesting other types of items like science technology, like game style weapons and all of this kind of stuff. So here's a little example of the types of objects that are in Objaverse. There are sort of interesting animated objects that are rigged characters. We have objects that we can separate into parts. There are large-scale vistas of the exteriors of cities and buildings. There are full like interiors of environments. And then, as you see in the sort of bottom row, there's just an incredible amount of diversity. For the simple sort of category of chair, we have things that look that go from being incredibly realistic on the left to wholly abstract and game-like on the right. And here is just an example of one of these animated articulated objects that could be of relevance for robotics. So you have fridges whose doors open. And so I'll be talking about observers mostly in the context of robotics, but of course it is useful for all sorts of other tasks as well. And so one of the early works using observers looked to use it to be able to do 3D object generation from a single image. And so this is pretty cool. It's a very fun sort of outcome that you can sort of potentially use. And in principle, you could also imagine, taking this out, taking pictures of objects that you see on the street, generating the 3D asset, and then maybe even also using that in a robotic setting. Okay, so that was scaling objects. Next, I'll move on to scaling scenes. And so, as I said before, when Thor originally released, it had around 120 scenes within it. In the couple of years following its initial release, there were some extensions to that, adding in another 60 and then another sort of 20. And that's great, but each time that we added these additional scenes, it cost quite a lot of money in terms of the time of technical artists and game designers. So you can design scenes. Another approach that people have taken to be able to generate embodied environments is to scan them. So here we have this Habitat Matterport 3D data set where they had people go out to these large home environments and grab the Matterport scanners, walk around, and actually do full 3D scans of them. And from that, you get a lot of diversity, but you also get a relatively static environment, since none of the objects, since all the objects are essentially baked into the underlying mesh. And so both of these approaches, again, they suffer from the same problem. If I want to collect more of them, if I want to scale, I need to either get a lot of more artist time, or I need to find more houses and actually go out into the real world and collect the data. So in comes ProcThor. So this is our paper on scaling embodied AI by procedurally generating interactive 3D environments. And so everything in ProcThor starts with an environment specification. So you can think of this as a bit of a template or a hierarchy of what you want in the home. And so in this example here, we have a home that has a bedroom, a bathroom, a kitchen, and a living room. So given this environment specification, we first sample candidate floor plans. And so here you see some of the variety that might be generated from ProcThor. Once we've selected the floor plan, we sample various object placements. So this includes large objects like fridges, tables, chairs, and also all of the small objects that you would maybe put on those onto those larger objects, like fruits, knives, forks, all of that good stuff. After you've sampled object placements that sort of respect the room types that they're being sampled into, you then sample lighting, sample materials, and then you're basically done. Now you have a fully interactive 3D environment that provides to you all sorts of interesting ground truth information in the form of instance segmentation, depth maps, and you can use to collect data. So here's just a quick top-level view of some of the variety of different environments that you can generate in ProcThor. As I said, these are all sort of indoor household environments. Great. And so, now we can generate all these scenes, but it's not necessarily clear that they actually are helpful. And so we have a host of different experiments showing that scale really does matter when we're training in these spaces.
8:50 a.m.
So, so in this first plot here, we trained an agent on sort of 10, 100, 1,000, and 10,000 scenes. This is all using RL, and then evaluated in sort of a set of unseen or manually designed testing environments, these architect Thor scenes. And happily enough, we saw that performance did increase quite dramatically as you scaled the number of houses and the amount of diversity that the agent was seeing. And these observations extended to a host of different evaluation environments. So again, these are all evaluation environments where the environments were not actually seen during training. So you can get very good zero-shot numbers doing this type of approach, but if you really want to get state-of-the-art or beyond state-of-the-art type of numbers, we then took the agent that we pre-trained in ProcThor and fine-tuned it on the training data set for each of these different data sets. And in RoboThor, we got a nice big boost there as well. So showing that this pre-training put the agent in a very good space to learn the biases that are sort of inherent to this environment. And we repeated that observation across a number of other environments as well, including this habitat sort of object nav task. So that was all navigation, so navigating to an object. We also showed that this worked for other more complicated tasks requiring object interaction. So there's this AI2Thor rearrangement task where the agent has to grab objects and place them into different locations. Fine-tuning, pre-training and fine-tuning led to state-of-the-art results there. And we also deployed this on this manipulathor arm point nav task as well. Okay, great. So I've talked about Objaverse, I've talked about ProcThor. So scaling scenes and scaling objects. The natural thing to do or to think you would do is just to grab all of these Objaverse assets and throw them directly into ProcThor. Then you get the best of both worlds. It's sort of all of these scenes with all of this diversity. Unfortunately, the order in which these projects came was sort of separate from the way or opposite of what I've shown in this talk. First, we came out with ProcThor, and then we came out with Objaverse. And so, there were some challenges to be able to get Objaverse into ProcThor. And the biggest of these were missing critical annotations in the Objaverse dataset annotations. So things that were missing included, scale, what is the actual number of, meters long that these objects are, their types, whether or not they're actually appropriate for indoor home environments, and then we were missing any priors on placements of objects, so where they should be put. And all of these things are critical to be able to use these objects inside of ProcThor. So to address this missing collection of annotations, we produced the Objaverse home annotation dataset. And so in particular, we got humans to manually annotate 40K of the most home-appropriate objects from Objaverse. And they included descriptions of the objects, object types, and scale. So once we have these annotations, again, we can't just take these objects and throw them into our simulator. These objects were generated by, arbitrary people on the internet, and we need to be able to put them into a consistent format and ensure that they are optimized. So if somebody scanned an object, for example, the polygonal mesh may be extremely dense, and if you were to put that into a simulator, it would be very, very slow. And so to be able to do this, make these objects consistent and also optimize them, we developed ObjaThor. So this is a package that's available in open source right now that can take in any GLB file. So this is a very common object file. And in just a minute or so, we'll be able to make that object usable within Thor immediately. And originally we developed ObjaThor mainly as an optimization framework to be able to make these objects, put them into a consistent format. But more recently, we've also built out a GPT-4V powered annotation pipeline. So now we can take any object, any GLB file that somebody gives us and generate these important annotations like descriptions, object types, scales automatically without needing humans. And to give an example of what these annotations might look like, here I took a GLB for a spot agent, asked GPT-4V through ObjaThor to generate a description, and you get something that's very, very reasonable. So this is a quadrupedal robot with a yellow and black body featuring articulated legs ending in black feet. And that's a sufficiently rich description to, for instance, get an agent to navigate to an object of this instance description. So ProcThor and Objaverse are, putting them together, you get a set of simulated environments that are fast, cheap, unbounded, and I probably should have also written diverse. So that's amazing. The one downside here is that they are templated. And so we would like, in principle, to be able to take these templates, these room specifications, like having 2 bedrooms, a kitchen, a living room, and a bathroom, and instead replace them with natural language descriptions of the environment that we want, right? So rather than just thinking about houses, maybe we want an arcade room with a pool table in the middle, or an apartment for a disabled person who needs to use a wheelchair. And so to be able to enable this, we built out holodeck. And so holodeck is a system that takes in natural language user queries as prompts, and then through a large system of like search and reprompting and interfacing with LMMs, we're able to produce environments that match that input user query and simulate them within Unity or AI2 Thor. So to give a little bit more detail on how this process all works, I'll talk about the generation flow. So the first thing that starts is we will generate floor plans. So here is an example where we're asking a LMM to generate the floor plan of a 1-bedroom, 1-bath apartment for a researcher who has 2 cats, and answer in a particular format. The LMM will very happily do this. It'll tell you that it needs a living room with bamboo flooring and light blue wallpaper, and then it'll generate the coordinates on the ground plane for that room, and it'll generate then, kitchen with black slate tile and moss green paint. And if you do that and then graph it, you get a layout that might look something like this. And so this is obviously, it's great, but how do we actually go from these descriptions of what these rooms should look like with the materials to rooms with materials in them? Well, we have a database of various types of materials, and through a clip similarity search, we're able to find the material that best matches the description, and then output that and apply it to the rooms in Thor. So I'm going to skip. And feel free to interrupt me at any time if there are any questions. So I'm going to skip windows and doors, but we can generate those as well. Maybe the more interesting thing is then to do object selection. And so here we are asking the agent to select large floor and wall objects for the scene. And the agent might respond something like, the living room needs a sofa, or on the floor, there should be a sofa, and the description of that sofa is modern turquoise sectional sofa. In the kitchen, there should be on the wall a pot rack, and it should be a wall-mounted stainless steel pot rack. And then using the same clip idea combined with our huge data set of objects in Objaverse, we are able to find pretty consistently objects that match these descriptions and then place them into the environment. So that was selection. And I said place them into environment, but this is actually a bit of a harder task than you might initially think. You could just simply ask the LLM to output coordinates for objects. When we did that, we found that oftentimes it would place objects that intersected or into sort of weird configurations. It did not seem to be great at predicting exact coordinates. So instead, what we did was a sort of constraint-based approach. So instead of saying, sofa at 3.3, it instead says the sofa should be on the edge of the room, when the coffee table should be in the middle, in front of the sofa, near the sofa, and centered aligned to the sofa. The floor lamp should be on the edge of the room, left of the sofa. And once you have these constraints specified for these objects, it's just a simple search across constraint space to be able to produce configurations that are sort of pleasing and respect the constraints. And we found that this constraint-based way of specifying locations really led to some very natural-looking environments, and was relatively easy to satisfy. Okay, so that was the generation flow. What does this actually look like once you've run it? And so here we asked the holodeck to generate 3 professors' offices connected to a long hallway. The professor in office 1 is a fan of Star Wars. Here you see that happily there are 3 offices. There is a long hallway. And then because of the large amount of diversity in these Objaverse assets, we're able to also respect the fact that this professor is a fan of Star Wars. Here are some other fun examples. So you have an arcade room with a pool table placed in the middle, and a garage with a red sedan, and a black bicycle. And so you can see, when it works well, it really respects the requirements that are given as input. There's a huge amount of variety in different types of indoor environments that are out there. And assuming that the objects are in Objaverse, you can generate all of these, right? So you can have a interesting hair salon, a pantry, a dental office, and many, many, many more environments. Thankfully, we do see that humans like these holodeck generated environments. So it's not that the LMM is just randomly throwing objects into a scene. And so in this set of experiments, we asked human annotators to rank holodeck scenes versus Proctor scenes on residential houses. So Proctor obviously can't generate anything beyond homes because it requires sort of manually written rules. And so here we're sort of giving Proctor the biggest advantage it could possibly have. It's generating exactly what it's meant to generate. And even then, holodeck generally outperforms, and people prefer its asset selection, the coherence of layouts, and just overall stylistically. So that was all about generation. We actually want to be able to use holodeck for things, and to be able to do that, we sort of pre-trained on Proctor, we fine-tuned on interesting, novelly generated holodeck environments, and then deployed agents into held-out scenes created by humans for those environments, and found that the agents worked better than if you were to just use the initially pre-trained Proctor agents. Okay, so that was scaling objects and scaling scenes. Finally, we can get to SPOC.
Quick question for you, Luca.
Absolutely, yeah.
So the generation pipeline here is entirely text-based, right? Or
Yes.
are you using the vision modality at all?
So this was the timing was such that it was the vision modality was not super available at the time when this came out. And so no, we're purely text-based for this, except for the fact that obviously we use clip to be able to match objects and get materials in this.
And do you feel there would be any gains by like prompting a VLM with the actual top-down view of the current app to kind of refine it or things like that?
Yeah, absolutely. I think the one downside is just cost. So it is definitely the case if you end up playing with holodeck, which I encourage everybody to do so. It will sometimes generate very weird looking scenes, and I suspect that GPT-4o or any of these good vision models will be able to look at this and say, this is crap. Let me you should regenerate. But yeah, the cost of it is a bit high when you have to reprompt over and over and over again.
Okay, so for holodeck, you had like a kind of a quality control at the end to make sure that the scenes made sense.
Yeah, so generally we didn't in this human preference type of experiment. Here we just use whatever we generate. But I mean, as you see, there are cases where Proctor is preferred, and so it doesn't always generate the incredibly beautiful scenes. It does its best. So I think you could imagine using GPT-4o or one of these things as a quality control to prompt regeneration, or even use it in the pipeline, sort of as you're generating, to pick new constraints or maybe pick different types of objects, these kinds of things.
Right. Okay, thanks.
Awesome. Okay, so SPOC. So there's a major underlying hypothesis for SPOC, and that is with enough data and diversity, we are able, or imitating heuristic experts in simulation enables real-world navigation and manipulation. And so I've spent the last couple minutes talking a lot about what we mean by data and diversity. So let's jump right into imitating heuristic experts in simulation and what that means. And so, like I said previously, one of the great benefits of simulated environments is that they have all sorts of really nice ground truth information that's readily available. And this means that if you want to write a navigation planner, you can just grab shortest paths from a nav mesh that's in the environment and have the agent follow those paths. Similarly, we know what the full room layout of the environment is. So if I want an exploration trajectory that goes to all rooms, I can just quickly plan a route through those rooms and then execute it with these shortest paths. If I want to do manipulation, I have all the object geometry. So I can write a planner that will position the hand or the grasper near the object to respect that geometry. I know the full 3D object location, set of object locations, as well as the exact position of the agent. And then finally, we know all of the spatial relationships between objects, all of their attributes. So if I want to have an agent find the broken TV, I know exactly where that is. If I want to have it find the largest mug in the kitchen, it is, again, easy to figure out where it should go. And so here's an example where we generate a trajectory. And again, these are easy to generate heuristic planners for, where the agent is going to the container that's closest to the ground. So here it looks at the first container and then goes to the second and then back to the first. So if we have these planners and we're able to generate interesting trajectories, the question is, what are interesting trajectories? How do we define tasks that we want to train our agent on? And the way that we've been thinking about this is to break it down into behavior and goal specification. So a behavior that you might be interested in is object navigation, so navigating to an object. And the way that you specify that object might change. So if it's a type, you would say something like navigate to the toolbox. But you could also specify it via an affordance. So navigate to the container that can be best used for carrying tools to different locations. It might be the instance description for a particular object. So navigate to the yellow rectangular closed toolbox with black metal strips. Or perhaps navigate to the largest toolbox. So those are the goals types of specifications, and given a behavior, of course, we have many other behaviors out there. So object navigation is one, but you might want to also pick up an object, fetch an object, which is, navigate, find, explore, and then grasp and lift an object. You want to grab that object and then bring it to a room, which is fetch to room, and some others. We also have a collection of additional navigation tasks that don't quite so cleanly fit into this behavior across goal specification. So things like conditional navigation. So if the toolbox is full, find me a cloth bag. We also have interesting exploration tasks and some more complex rearrangements. So fetching multiple objects and placing them in multiple locations. So we're able to generate. Oh, yes, please.
Yeah, good question. So at what level does, last time I checked, I think AI tutor does not support like the low level physics for manipulation, right? So it's, at what level do you support manipulation in this simulator?
Yeah, so Thor with the current stretch agent that we have, it supports some level of manipulation, but it's certainly not the context-rich type of manipulation that you would get from like MutraCo or one of these other simulators that are out there. And so you can like knock over objects, you can push things, do all this, but the grasping that we have is definitely simplified. So you need to place the grasper so that sort of it is around an object or touching an object, and then just take the grasp action. And then we actually deploy this in the real world. We have a little bit of a heuristic that'll execute that grasp given that the grasper is right next to the object.
Gotcha. Okay.
Awesome. So like I said, we have all these interesting tasks, and we have these planners that allow us to generate trajectories for those tasks. And so now we are able to actually generate our data set. So we call this chores. So this is both a benchmark and a training data set. And this is open vocabulary. It has data from over 100,000 different houses, objects with 500 plus different categories, 10 million training episodes, 100 million plus training frames. It's multitask, and it's all using this stretch RE1 agent. And I should say one thing that's interesting and a bit different if you've ever played with the stretch agent. Here we have mounted 2 additional cameras onto the agent. If you look at this graphic here on the top, and that's because we want to remove the need for sort of active perception where the agent needs to move its camera. So we just have one camera facing forward that's along the navigation forward axis, and one that's 90 degrees perpendicular to that, that's along the sort of arm direction. So the arm is, if you've never seen the stretch before, it's a bit weird. The arm is 90 degrees to the forward direction. Awesome. So this is what one of these trajectories in our environment in chores looks like. So we have the instruction to find a bowl and grab it. And on the left, you have the navigation camera, and on the right, the manipulation camera. So the agent sort of walks through this ProcThor environment with Objaverse assets in it. And as you'll see here, there's kind of a fun, weird Objaverse asset that's been placed, like this huge boulder. Then the agent sees the bowl. It sort of positions itself so the manipulation camera is facing that bowl. It executes the actions to be able to move the arm out, and then it eventually grasps it. Okay, so now we have the data that we want to imitate. We'll need a model that actually does the imitating, right? Like the agent itself. And so what we do is we have an RGB only agent, and at every time step, we're going to input to that agent a language goal description of the task, the set of camera frames, again, RGB only, from this navigation and manipulation cameras. And these are going to be passed through pre-trained and frozen text and image encoders. So these are these large visual foundation models that are all the rage. So we encode them with these pre-trained encoders and then pass them through different MLPs. And these MLPs map all of these different tokens into a shared embedding space. Once we have that, all these tokens in the shared embedding space, we're able to pass it into a non-causal transformer encoder, and along with a additional CLS token. And then we take the representation corresponding to that CLS token as the sort of goal conditioned visual representation for the current time step. So for current time step t. And then we want to actually use that time, multiple time steps when making decisions about where we're going and what we're doing. We'll feed that current time step along with all previous time steps into a causal transformer decoder. And it has to be causal, obviously, because you shouldn't be able to attend to observations from the future. And from that, we generate actions. And that can be used to imitate the ground truth trajectory. Training with this type of transformer model in our setting came with a bunch of different challenges we had to solve. Should see the paper for a discussion of all of them, but one of them was sort of training with long horizons. So the tasks in chores can be up to 1,000 steps long. And you obviously don't want to be able to or fit all of that into memory when you have these like relatively large transformer models. And so what we do during training is that we will take this full trajectory, we will just randomly sample a sliding window of up to 50, 100 steps within that trajectory, and we'll just train on that randomly subsetted window, with some additional augmentation. And then when we actually deploy the model, we'll evaluate it, allowing it to see the entire trajectory. And this ends up actually working quite well. So the model, despite being trained on only 50, 100 steps of experience at a time, is able to generalize when you have up to 1,000 steps of prior observations. Okay, so just to summarize, we were training on shortest paths. These look like this. And you get agents by doing this that are able to explore when deployed, right? And this is really interesting. Generally, you would not expect imitation learning agents to be able to generalize and perform backtracking behavior when they've only seen sort of ground truth shortest paths. But nevertheless, this actually works quite well, and we see some really exciting and interesting behavior. One of these interesting behaviors is that SPOC understands spatial relationships. So here we ask the agent to navigate to the highest fruit in the kitchen, and you'll see that it walks around this kitchen. It sees that that's a living room, moves away, finds this like set of bananas, and then goes back to what it saw originally, which was this apple sitting on the kitchen counter. It's also able to perform task-specific behaviors. So here it needs to locate a computer on a sofa. It sees a sofa, sort of ignores it because there is no laptop on it, then walks around and eventually finds the correct sofa with a laptop on it. And none of this would actually matter if it didn't work in the real world. And so here we have an example of our agent fetching an apple in this sort of apartment environment. And the agent is able to explore, move through multiple different rooms, down a hallway, and eventually executes the grasp successfully. Here's another fun example where the agent is trying to find a toilet. And so it is walking around, and this really shows some of its exploration abilities. It enters the kitchen, realizes that it entered a kitchen, and that's probably not the best idea. It goes into the hallway, starts walking down, and then you'll see in this manipulation camera on the bottom right that it sees the bathroom on the right side. And so then it realizes that, turns, enters the bathroom, and finally, after some navigation failures. And here's one final example, which is kind of a fun failure case where the agent is attempting to pick up this houseplant. Its gripper gets stuck initially. It adjusts for that. and then it reaches out to grasp the houseplant. Initially, it will sort of go down too early, so it misses the plant. And then it tries again, and then rather than grabbing it in the appropriate location, it instead just picks the plant sort of out of the pot, which I suppose is technically correct, but it isn't exactly what we would want in the real world. We ran a large number of real-world sort of qualitative quantitative trials on this agent, and we see that it works quite well in the real world. So for tasks like object navigation, we get 50% success. For these more complicated fetch style tasks, it's still not above 50 quite yet, but it is certainly trending in that direction. We ran a number of ablations to understand better what was contributing to performance. So things that mattered were the number of training episodes, the diversity of the houses, the size of the context window. Very important, especially for real-world transfer, was the visual encoder that we were using. And then finally, the architecture using these sort of transformer encoders for the visual observations is really important, as well as the decoder. Although really what we see from this is that the things that were really driving performance were scale and diversity and using powerful visual models. And you get some additional performance boosts by using these transformer decoders on top. But really, the big gains are being driven by scale and diversity. So I should say there are some failure cases. As I said, we're getting 50%. So what do these look like? What we ended up seeing in many of our experiments is that the agent would simply not recognize the object that it was sort of trying to find. And to validate that this was the case, we trained another agent that had ground truth bounding box detections as input. And by giving these ground truth bounding boxes, you can see huge improvements across the majority of the tasks that we were testing at the time. So object navigation jumps up to plus over 80. Pickup style tasks where you're already looking at the object don't improve that much, but then the fetch style tasks where you have to navigate then pick up jump up again like hundreds of percents or multiple times over. The nice thing is that you can take a model that's trained with these ground truth bounding boxes and then also deploy that in the real world. And if you do that, you also see these huge boosts. Here we're using an open vocabulary object detector, this DEDIC model, and find that it works really well. You can actually just take these models that are given ground truth information at training, deploy them with noisy detections at evaluation time, and get big boosts in the real world. Okay, so that was SPOC. It's a shortest path Oracle clone. It is able to be trained using RGB only. It is proficient at long horizon tasks. Our code, data, and pre-trained models are available now. But I would be remiss to say that this is something that we did at CVPR 2024, and we've had a bunch of progress since then. So I want to have spend a little bit of time on what we've done in the last couple months as well. So I want to talk about PoliFormer. So here we're coming back to RL. To training some agents with transformers. This was one of the sort of top 8 best rated papers at Coral. And well, I guess we'll be presenting it in about a month. And then I also want to end with Molmo. So this is our released just last week family of open state-of-the-art multimodal models that are really relevant for robotics. So PoliFormer, here we're really focusing on building mastery within a particular task, and that's for navigation. And so why are we going back to RL after claiming that imitation learning was the way that we should be doing things with SPOC? I mean, the problem really here is that we have these nice results, but none of these numbers that we have are above 90%. And if you want these agents to be deployed in the real world, you want mastery. You need these agents to be incredibly reliable. And we know that RL is able to build really masterful agents when it works well. So AlphaGo, these types of things, the only place that we see really superhuman performance is when we are using RL. But unfortunately, it is slow and relatively hard to use with these transformer-style architectures. And so this PoliFormer project is really about allowing fast and stable RL with transformers. Some of the key ideas here were to use hundreds of parallel rollouts across these diverse Proctor Observerse style environments. We implemented a new sort of SPOC++ architecture. So it's very reminiscent of SPOC, but it makes some key architectural changes. And these include things like including a KV cache. And that's just one of the many levels of caching that we included that allow training FPS to be high. So if you don't do any caching, you get maybe 100 FPS when training. If you sort of implement multiple levels of caching at different layers, you're able to get, for some embodiments, over 2000 FPS during training. And what we ended up seeing with this project is that, perhaps not surprising, but the performance just improves continuously with scale. So as we go from 10 million to 100 million to 700 million steps of training, performance keeps on going up. And this is on the validation set. While we only had so much budget to run these models, it looks like it hasn't saturated yet. If we just let this trend continue, we fully expect that it would continue going up. And so here are some of the examples of how SPOC performs with respect to PoliFormer. So previously we had SPOC, barely getting above 50% in this object nav task, and the PoliFormer model is able to get over 80%. It basically ties the performance of SPOC that was trained with ground truth object detections. And if you also use object detections with PoliFormer, you get another nice big boost. So here are some fun examples of deploying this PoliFormer model. Again, this works without any adaptation in the real world. So here the agent is looking for multiple objects in sequence: a sofa, a toilet, a houseplant, and a book. Then we have a deployment with this localbot embodiment, and you'll see if you look closely that a chair is sort of dynamically added, and the agent is able to sort of handle that despite it just sort of magically appearing, and eventually finds an apple. Some other fun things. So if you train a model, one of these PoliFormer models, and give it no text description, only boxes, so it's a box-only model, you get something that's called, what we call box nav. And if you train in this way, you can deploy the agent to go to boxes of around objects it's never seen before. And so this allows us to do things like get the agent to follow a toy car around an office building or around our back door apartment. You can also have it follow a person. And again, it never saw this during simulation. And then you can also sort of string together multiple of these boxes to get the agent to do multi-object navigation or find a room or do open vocabulary object navigation. And then we've also played around with using this box-style agent in hierarchies. So here we have some, GPT-4o style models sitting on top, saying whether or not an object is of the correct sort of description. And we're asking the agent to, find a book titled Humans. And so it runs around. It initially started looking at a book that was not titled Humans. It ignored it and eventually found this book. And if you look closely, it indeed does say Humans on it. So like, as I said, RL works when it works really well. RL builds superhuman performance, or, at least very good performance. But when it doesn't work well, it can often simply just fail to do a task at all. So for this fetch style task, the PoliFormer model gets 0 performance, even with dense rewards. And so we recently had sort of a follow-up work by an internet AI2 building out Flare. And the idea here was to take the baseline decent models that we have trained via SPOC-style approaches, and then figure out how to stably fine-tune them with RL. And I encourage you to look at this paper. It's pretty interesting. We're able to use just sparse rewards and make some smart adjustments to how we are training these agents to build really, really impressive performance. And so here, it matches object nav performance for the original PoliFormer model, but if you look at this fetch number, we're able to get dramatically high numbers when previously PoliFormer completely failed to train at all. Okay, so that was the PoliFormer style line of work. Finally, I want to end with some discussion of Molmo. So this is our family of open state-of-the-art multimodal AI models that can point. And if anybody is on their laptop right now, I would not be insulted if you went to this web address and started playing with this model if you haven't already. And so the idea here is that the existing advanced multimodal models are proprietary, and we're really not or there's a lot of missing information about how to build performant visual language models. And if we look at the differences between sort of the best proprietary versus the best fully open models, there is a dramatic gap. So here are some of these API-only models, and we compare them to the fully open models. And it's not even close when comparing numbers across these academic benchmarks. And if you consider models that are, not truly open in some sense, but are using data that they don't release, you get models that perform better on these benchmarks, but even still are not matching the performance generally of the API-only models. So in comes our Molmo model. So these are fully open data training, all that good stuff, models that achieve sort of state-of-the-art performance when averaging or looking at these academic benchmarks at relatively small sizes. And these academic benchmarks are great, but you also want to get some notion of how do humans prefer these models, and we see even there these Molmo models excel. And so we released Molmo last week, and basically 2 hours later, Llama 3.2 came out. So there was a bit of a mad dash to compare our model with Llama 3.2. And even there, our 70B model outperforms the best competing Llama 3.2 model. And this is despite the fact that we are training with a dramatically smaller amount of data. So not billions of images, but just hundreds of thousands. And the reason that we're able to do this is that rather than using these really simplistic captions that come with standard web-style data sets, we instead get annotators to speak about images for 60 to 90 seconds, and they produce these extremely rich descriptions that describe all sorts of parts of objects. And a really critical piece of Molmo that makes it applicable to robotics is that we also have trained this model to be able to point, so to ground its sort of outputs with points in the image plane. And so here's a fun example of this. So we ask Molmo to point to the handle on the white bottle. You can see this pink dot appear on the white bottle. Then we deploy an agent that goes and executes a grasp on that point. Next, we ask to point to where I should put the dirty dishes, and it'll generate a point on the sink. It then walks over there, and now we can ask where there is free space in the sink. And then finally, we will execute that final place policy to put the object into that position. And so I'm really excited about Molmo and its future applications to robotics, and wanted to end by just thanking all of my collaborators. So we have this big SPOC team. I talked about a whole bunch of papers, so those were listed on the left. And then the Olmo project was a huge collaboration. So it was too many authors to just simply write out. I've included a screenshot of the archive paper there. So thank you so much.
Thanks, Luca. Okay, questions?
I have a question. So you seem to be like really against depth.
Yeah.
I'm wondering why.
Yeah, so I think we want to push the capabilities of what is possible with RGB. So I think RGB sensors tend to be very good. There's no problems with sort of destructive interference, any issues there. We sort of understand how to perform augmentations on them. They're very fast to generate within our environment. So there are a bunch of sort of practical reasons. I think the more philosophical reason is that as originally vision researchers, we want to see how far we can push RGB only. But I should say we do have some projects that are playing around with depth. So we're not against it. I think it will be probably necessary if you want to have very good sort of contact-rich manipulation style agents, or agents that need to, grasp and rotate and do all that kind of stuff. For these more navigation style tasks, it doesn't feel like it should be necessary.
Probably not necessary, but would dramatically
improve,
lower the difficulty, right?
So I should say with this PoliFormer style model, yeah, okay, it probably can reduce the difficulty, but we have not found it to be sort of an easy plugin. So we have played with this. Figuring out how to sort of encode these models is not super trivial, especially if you want to sort of merge this information with RGB. So we've seen some progress, but usually the benefits that we find with depth is that you might have a slightly lower collision rate, or something like this, where it feels like if you just penalize the agent enough, you can probably get the same sort of behavior without actually including sort of these depth sensors, without needing to have them on the robot. especially if you want to use something like a GoPro camera or something, you don't have depth that's sort of well aligned with RGB. So I take the point, but I think if we can get it working with RGB, it's sort of the holy grail, let's say.
Okay, yeah, I buy that.
Got a question. That's all right. I guess it was a quick one because you were talking a little while back about the window size for like the history you're keeping for, I think, even the SPOC model.
Yep.
And to kind of talk about this a bit more, because I know one of the tricky criticisms a lot of foundational models for robotics have been getting is, okay, you're doing this over like 20 time steps on average in the data sets. So I was surprised. Well, I mean, in one case, do we really need to have it work over 1,000 time steps? Because was there really that much information you need to store about the history? Or do you think like extending those time steps is going to be important for more interesting robotics problems?
Yeah, I think probably I think we can't get away from the problem that we need information from many time steps ago. So if I'm navigating a very large home, so we have Proctor homes that have 10 rooms in them, you're not taking large enough steps that would mean that you can sort of find the target within 50 steps or something. You really need to deeply explore and look around a lot. And then if you want to avoid backtracking to exactly the same rooms, you need to know that the room on my left is one that I've gone to and that the room on the right is one that I haven't. My expectation is that we need better ways to sort of sub-select experiences or summarize the information that we've had in these long time horizons. The amount of actually important information is relatively small, and you're wasting a lot of compute by trying to sort of think over all of the previous time steps again. So I think it's sort of a mixed answer. I don't think we need all the information, but we do need to be able to look at all the information, or at least do some sort of retrieval-based approach to be able to think about it or summarize it.
Yeah, I mean, good point. I mean, that's kind of the rule of thumb people are using lately is like, well, we know we're wasting 90% of our compute on like one bit of data that might be helpful, but we like doing this because it works rather than maybe a more complicated solution.
I think the depressing thing is that whenever we've tried something more complicated and then you just stick everything into the transformer, it's always worked better just to stick everything into the transformer if you can afford it. And so it's very it doesn't feel tempting to play around with complicated or more sophisticated solutions, even though honestly that's sort of my bread and butter. That's where I came from. I really loved building all these really complicated models back in the day. But yeah, I think the bitter lesson is definitely true. Just get more data, get more compute, and you can often do some pretty amazing things without thinking too deeply about the problem. We'll see if that sort of asymptotes in the near future.
Okay, thanks. I'm good. I mean, I won't tell my students that or promote them so deeply, but
no, I mean, I should say obviously not everybody has access to tons of compute, and so we need models that are in robotics where you want to maybe even run these models on device. And so unless everything is going to be through an API, we need fast, good models that are more complicated and more intelligent with less compute, I guess.
Yeah, thank you.
Okay, one question, Luca, if you have time, if you have
Absolutely.
to go, I can. Okay, cool. About the SPOC agent. So I'm just wondering, say you condition the agent on like an exploration sequence. Do you notice like that it gracefully switches to like an optimal behavior where it starts like navigating, taking clear shortest paths when it's already explored the environment? Does my question make sense?
Yes, yeah, no, definitely. So we haven't, so basically, I guess to repeat, the idea would be that we sort of push or allow, guide the agents along an exploration trajectory, maybe like looking at all the objects in the house, and then we just ask it, go to the banana or something, and then it just runs over and hopefully would find the banana.
I'm just wondering if it can like automatically switch between exploration mode and exploitation mode.
Right. So this is not something, surprisingly, that we have actually evaluated. We've done a bunch of like sort of qualitative looks at the behavior of the agent in terms of how it explores and how it runs around and backtracks. It is certainly not the case that it's perfect. So there are times where it will sort of miss seeing a door and then just run back and forth a whole bunch and not actually go to the room that it needs to go to. But that's a bit different than your question. Your question would have sort of already shown the agent that you could walk through that door, and that's not something that we've tested yet. But is a really cool idea. We should definitely do that.
All right. I think that's it. Thanks so much, Luca. That was a great talk.
Awesome. Thank you so much. Great to be here.
Okay. See you.
Bye.